Bruh. Bruh. What is it? Almost 5? Crazy. Honestly, this should not be its own page. I feel like I can just add it to here, or honestly, all of these can be its own page, just this section. I don't know what to do with this. Because I don't want to name it this. What would it be? That's too generic. It should be like cloud contract business requirements. It's also just like a tiny section. This whole thing can go to here. This will be its own page. And the other ones will probably be their own page as well. As far as I can tell. So it's really just this. Vendor business requirements, maybe? Or business requirements for cloud contracts? Yeah, I like that one. Just because I don't care. I just need to move on. It's not really an important section. I'm probably not really going to review that too much. I just want this minimal info to study from. I like that. Oh, I already forgot what it was. Business. Shoot, what did I just say? Useless, man. Business requirements for cloud contracts, for cloud vendors? For cloud vendors. Maybe that. For business requirements for vendors? No, for cloud vendors. Yeah, I'll just go with that. For take that here as well, actually. Yeah. I don't know, not too important, but goodbye. And then this, I can just like just put it into here, basically. This is focusing on risk assessments, vendor management concepts. Okay, no, that's fine. Yeah, that's fine. It's just focusing on risk, which essentially is what it is. Vendor due diligence. Conduce due diligence. Evaluating selecting vendors based on, yeah, so that, okay, I already have that basically. I don't have vendor locking in here, so I gotta add that as a risk. Periodic assessment, that's this. I'm just gonna keep also this though. Yeah, that's fine. Maybe this goes here. I'll just add that there. Risk identification, or maybe actually put that in risk. Engage vendors. No, this section. Oops. Okay. Yeah, that's fine, whatever. Okay. Bam, gone. This... Oh wait, I forgot to link that. What was it? Vendor management? This I think is going to be better, way better. Now I can create a vendor management life cycle. Should that be under here? It could be, honestly, but I'm not gonna worry about that. I'll just have these broken out instead. But honestly, whoa. have this. The worst part is like when there's kind of redundant information, conflicting, I should say, overlapping, something like that, where you have like the same idea from two different perspectives or focusing on two different contexts of information regarding that concept, and then they kind of like don't fit well together. That's the hardest way, because usually I try to minimize all redundancies by combining everything and refactoring such that it's like one atomic concept, but sometimes it doesn't really work too well, or they don't work nicely together. So in that case I don't care. Sometimes it's just not worth the work of doing that. And the best tip is like you can always just do it later when the need arises for it. If there really isn't a major need for it, if it's not causing problems, then it's probably just fine to leave it as it is. So that's what I'm gonna do. It's probably just best to do it this way. This one's not really detailed, so that's fine. There's probably not going to be too much in here to take notes on. Evaluate security. Quality. What did I spell? Evaluate. Quality. Nothing, this is not really, I don't know, these notes, there's nothing really here. This is just kind of like common sense, I guess. Nothing really to take note of in this. I don't know. I don't really need any of that. It's kind of whatever. Bro, how many times am I gonna unsubscribe from Mapbox and still get emails? Unreal. I don't know, nothing even in here. That's the only thing. Whatever. Too sparse. This textbook is, I don't know, it's pretty sparse in a lot of areas. I mean, it's more like a study, what is this? Yeah, it's a study guide, that's why. So, I don't know. I prefer the Common Book of Knowledge because I read the SSCP one. That one was really good. I liked that one because that was pretty in-depth. Like, you learn stuff from that. This study guide version is, I don't know, it's just sparse. But it's faster. It's way faster. And I guess you just get, like, the bare essentials of what you need. So, I mean, it's a trade-off. But I prefer for long-term, the more in-depth stuff, because you learn more, take better notes, and it's just better for long-term. But if you just want to, like, go quick, then I guess the study guide's better. I don't know. I might do a really short stream today, obviously because I started late. If I started at like 12, then I'd already be like 5 hours in, but I would have been done already with my chapter and everything here, and I'd be doing the video review, which is what I'm going to do next. But I think what I'm going to do, because I'm probably going to finish this chapter in the test coming up soon, and then I'm going to probably eat, because I'm starting to get hungry. So I think I'm just going to end it, and after that, I'm just going to be like playing the videos offline. I think I might do that, because I also kind of want to, it's almost 6, it's going to get dark around 8 or 9. I kind of want to go on a walk or something, I don't know, get some steps in. So,
is... Okay, welcome to this lesson where we're going to talk about Domain 1 of the CCSP exam. So we're going to zoom through this pretty quickly. The only objective here is going to be to introduce Domain 1, which is covering cloud concepts, architecture, and design. For the CCSP exam, this specific domain is going to be 17% of the exam, which is relatively similar to the other ones. Specifically, this domain is going to cover a lot of key terminology. So you'll notice during this first module that there's going to be a lot of definitions, and it's certainly the most important for setting a foundation to understanding key terms going into this exam. Some of the key concepts we will cover is going to be introducing basic cloud architecture, as well as cloud enabling technologies, and finally tying these concepts into business functions to make sure that we're not just building infrastructure for the sake of building infrastructure, but that we're building it specifically to support the overall business. In summary, we talked about the introduction to Domain 1, which is cloud concepts, architecture, and design. Welcome back to this lesson on cloud computing definitions, roles, and responsibilities. In this lesson, there are 4 main learning objectives. The first one is to define what is cloud computing, and this is going to help us understand at a core concept level what this entire course is about. And then beyond that, we're going to dive a little bit deeper into specific concepts within cloud computing, such as service and deployment models. And then following that, we will discuss some roles and responsibilities for different contributors and stakeholders that might be dealing with the cloud. And then once we define those roles and responsibilities, we're going to define the shared responsibility model, which is who is responsible for different security and components within the cloud. So right away, NIST has a very specific definition for what cloud computing is, and that definition includes these 5 components of cloud computing, and of course that it's centrally managed and distributed access to IT infrastructure. Those 5 concepts are on-demand self-service, broad network access, resource pooling, measured service, and rapid elasticity. We're going to dive into these much deeper at a later lesson of the course. So right now, just take note that these are really key concepts for what makes cloud computing, as opposed to just renting out hardware infrastructure to another organization. Most cloud service providers have a variety of different services that they provide, and some may only have services in 1 or 2 of these categories. But most of our key players in the field right now, such as Amazon Web Services, Microsoft Azure, and Google Cloud Platform, are going to have a variety of services that fit into each of these different service models. And once again, we're going to dive into this much deeper later on in the course. But the key thing to understand here is that at this end of the spectrum, where we have infrastructure as a service, or IaaS, our systems are going to be much more customizable. But that also means that where the customer is responsible for customizing, they're also responsible for customizing securely. Platform as a service sits in the middle here, and we're going to see a variety of different levels of responsibility on the customer. And then on this end of the spectrum, we have services that are built to be more convenient for the customer. So there's less opportunity for customization, but much simpler to set up and use for the customer. Beyond the service models, there are 5 commonly referred to deployment models for infrastructure in the cloud. And once again, we're going to go into these in more depth later on, but right now we can take note that these service models are public, private, community, hybrid, and then multi-cloud. And for the most part, I think these names are actually pretty intuitive. For example, public cloud is going to be on public cloud infrastructure where you might be sharing the hardware with other organizations that are also using that cloud service provider. And then of course down here we have hybrid, which is just going to be essentially some combination of any 2 of these, I should say, categories. And then multi-cloud is when you're using multiple cloud service providers. Okay, so in this section, we're actually going to get into it, and we're going to define the 5 different key roles and the responsibilities that these roles have in the cloud. The first category is cloud service customer. And in most cases, this is going to be your role in building infrastructure in the cloud, is that you are going to be the cloud service customer. But something to keep in mind throughout this course is that in some cases, the CCSP exam expects you to consider yourself from the perspective of being the cloud service provider, or even some of these other categories. Most often, we're going to be thinking about these 2 up here, but it's important to understand that while you may be in a position that you are most often the cloud service customer, the CCSP exam is going to have at least some questions where you need to pretend that you are the cloud service provider. So starting with the cloud service customer, this is an individual or organization that contracts and uses services provided by a cloud service provider. The cloud service provider is an entity that offers and delivers cloud computing services to customers. So again, keep in mind that if an organization offers an opportunity to partially use some hardware that you don't physically own, that doesn't necessarily make it a cloud service provider. But if they meet those 5 key components of what is cloud computing that NIST defines, then that is what would actually define them as being a cloud service provider. Some other lesser, perhaps known stakeholders here are going to be the cloud service partner, which is an organization that collaborates with a cloud service provider to enhance or distribute their services. So this is going to be organizations that sell their services and helping another organization to build infrastructure in the cloud. So in this case, they are neither the cloud service customer because it's not their infrastructure, but they aren't the cloud service provider either because they're not providing the infrastructure. What they're doing is partnering with an organization to build cloud infrastructure that they then pass on to that organization to maintain long-term. The cloud service broker is going to be similar if you're familiar with an insurance broker. Basically, they're going to come in and they're going to evaluate different cloud service provider options or even specific cloud services. And then they're going to simplify that for the cloud service customer to present it in a fashion that makes it so they can very easily evaluate which one of those either services or cloud service providers are going to be best meeting their needs. And then finally, we have regulators, which is authorities at various levels that are going to be setting and enforcing standards and regulations for both cloud service providers as well as customers. Okay, so specifically between cloud service provider and cloud service customer, which are some of our core contributors in this case, we need to discuss where the responsibility lies between these different parties for securing and building cloud infrastructure. So for purple, we have the cloud service customer, and then we have this green teal color for the cloud service provider. And something really important to highlight right out the gate here is that up here we have data, and between IaaS, PaaS, and SaaS, data is always going to be the responsibility of your cloud service customer. Whereas down here, we have physical security, and regardless of which service model we're using here, physical security is always going to be the responsibility of the cloud service provider. Between here, we get some variability, and in some cases, you can see here that even some levels of responsibility here are split between the cloud service provider and cloud service customer. And then these smaller circles here represent maybe a little bit less responsibility on that party, or maybe just less likely to have that responsibility, because these categories for service breakdown are so general that in some cases it's really hard to draw a hard line in the sand as to whose responsibility certain configurations are, because there's a lot of variability in what services exist within these categories. So behind data, you have this identity and access layer, and you can see that almost always the cloud service customer is going to have some or most of the responsibility for managing the identity and access, but in some cases, the cloud service provider does manage some of that. And most of the time, that's going to be referring to identity and access of systems, where your cloud service customer is usually going to be responsible for handling the identity and access of people. And then below that, we have application security. And again, with infrastructure as a service, you're going to see that the cloud service customer is still responsible, whereas with both of these other service models, it can be a little bit mixed. And then network security is where, for PaaS and SaaS offerings, that largely cuts over to the cloud service provider. With IaaS, however, it could still be the cloud service customer's responsibility. And then finally, with host infrastructure, this is dependent heavily on the service that you're actually using within this IaaS category. So for example, for an Amazon Web Services EC2 instance, the customer is going to be responsible for managing the host security on the operating system and making sure that it's kept updated and secured and that kind of thing. However, the cloud service provider is still ultimately going to be responsible for managing the hypervisor and the infrastructure that instance is sitting on top of. Okay, so to summarize that, I think the way that I like to think about the shared responsibility model specifically is that if the customer can configure something, the customer is responsible for configuring that thing in terms of security. And the reason I say that is because if the cloud service provider is responsible for securing a particular component, then they're not going to make it an option either in the web browser or the command line interface. They're not going to make it an option for the customer to configure that because it is their responsibility to both configure that and ensure that it stays secure and configured. So the cloud service provider is responsible for giving you a platform on which you as the customer are capable of securing your components, but they're not necessarily responsible for doing it for you, only giving you the opportunity to configure that. Which again is why I say, if the customer can configure something security-wise, they are responsible for configuring it. Okay, so in summary for this lesson, we went over a couple of key components for what makes cloud computing, which is those 5 key concepts that NIST defines as being part of cloud computing. We then talked about service and deployment models such as IaaS, PaaS, and SaaS, as well as public, private, and hybrid cloud, that kind of thing. And then finally, we went over some key roles and responsibilities that we're going to be seeing in the cloud, and then specifically dove into where the responsibility lies between cloud service customers and cloud service providers. Welcome to this lesson on key cloud computing characteristics. As promised in the last lesson, in this lesson, we're going to do a deeper dive into the 5 cloud computing characteristics as defined by NIST. So first, we're going to give a quick overview and recap of those, and then we'll go into the definitions of each of those characteristics. And then finally, we're going to touch on a concept called multi-tenancy to help establish that for future lessons. All right, so as a quick recap, the 5 key characteristics as defined by NIST SP 800-145 for cloud computing are on-demand self-service, broad network access, resource pooling, measured service, and finally, rapid elasticity. So getting into these definitions, on-demand self-service is going to be the capability for users to automatically provision and manage resources without human intervention. So what this means is that if I log into Amazon Web Services or Microsoft Azure, I'm going to be able to spin up resources without contacting some sort of human that works at either Amazon or Microsoft in this case to help me provision those resources. So that means it's on demand and I am able to create those services by myself. Broad network access is the concept of resources being accessible from various devices and over the internet using standard protocols. So this is talking about mostly, HTTP and HTTPS, which allows you to access those resources via your web browser, but also being able to configure resources to be accessible through common remote access protocols such as SSH and RDP. And then next up, we have resource pooling. And this is referring to the ability of multiple users to share a pool of resources that are dynamically reassigned based on demand. So what that means is that a cloud service provider is going to have a massive data center that they manage, and many different end users are going to be sharing the physical hardware resources that are existing and being managed at that data center. And those resources are going to be dynamically reassigned to the different users based off of what those users are asking to be using. Next up is rapid elasticity. In this case, resources need to be able to quickly scale up or down based on requirements. And this is critical for the efficiency of resources in cloud. So that means that if you're able to take an EC2 instance or an Azure virtual machine, and you're either able to scale it up, meaning making that instance more powerful, or down and reducing the hardware that is supporting that infrastructure based on whether or not you are utilizing the full capability of those resources and whether or not you need it. And then finally, we have measured service. And this means that for a cloud service provider providing these services to be considered a cloud service provider, they need to be able to monitor and control the resource usage. And what that means is that they're able to use those metrics to provide transparent billing and reporting. So if you were using a cloud service provider, but they were not able to keep track of how much resources you were using, then that is a critical failing in that service provider. When all of these 5 things exist together, that is when NIST considers a service to be a cloud service provider. Next up, we have this concept of multi-tenancy. And this is actually an additional characteristic beyond those initial 5 defined by NIST that is recognized specifically by ISC². Quick definition of multi-tenancy here is going to be shared resources for multiple clients with some sort of logical separation, whereas single tenancy is dedicated resources for a single client. So we have these different visualizations that we have down here, and something I wanted to capture between these visualizations is that both of these are actually an example of resource pooling. In both of these, the cloud service provider can own the hardware. By the cloud service provider being able to centrally manage that hardware, it's still a pooling of physical resources that is managed by a centralized organization. And then a distributed set of customers are able to use those resources. The difference between these examples is that we can imagine these little horizontal boxes is a physical system. So a server that's being slid into a server rack in a data center. In the case of multi-tenancy, we have different cloud service customers that are all going to be running workloads on that one physical server. And the cloud service provider, in this case, is responsible for a logical separation between these customers. So these are different workloads that these customers might be running. And in this case, these little people might even be users of those applications. The cloud service customer is running on that infrastructure. But in this case, the hardware infrastructure is all shared, and there's just a logical separation to make sure that these workloads can't interact with each other in ways that they're not allowed to. Whereas over here, and this might be an example of the private cloud deployment model, which means that you're using a cloud service provider that is managing your physical infrastructure, but you as a tenant in that data center have a dedicated hardware server that is running your workload. So you can see these boxes are smaller, not necessarily to indicate less power, but just because I wanted to show that there are specific and dedicated servers that again might be slid into a rack that are supporting each of these customers' workloads. So this is single tenancy, where one physical server supports one customer, and that is a private cloud deployment model. Whereas this is going to be a public cloud deployment model, and it's an example of multi-tenancy, where multiple different cloud service customers are sharing physical hardware, and the cloud service provider is responsible for logically separating them. Okay, in summary, we talked about the 5 key characteristics of cloud computing, and we defined those 5 characteristics as defined by NIST. And then on top of that, we talked about that additional characteristic that ISC² considers, which is the concept of multi-tenancy. Thanks for watching. I will see you in the next lesson. Welcome to this lesson on building block technologies. In this lesson, we're going to talk about virtualization, storage, and databases, and then finally, we're going to talk about networking and orchestration. Okay, so jumping right in, virtualization is a super critical concept that even makes cloud computing possible. Virtualization is easily one of the most critical inventions in the IT world, maybe since its existence, and it is what makes it so that we're able to maximize hardware resources and physical infrastructure by logically separating systems and workloads on top of that physical infrastructure. So over here, we have this visualization of what standard infrastructure looks like. So you might think of this being your desktop computer that is sitting at home is going to be the physical infrastructure. On top of that desktop computer, you might have an operating system installed, which is going to be probably either Microsoft Windows or Apple's Macintosh. And then on top of that operating system, you're going to have a variety of different applications that are installed, such as Google Chrome or Safari or Steam, something along those lines. But those applications coexist and run kind of alongside each other on top of your operating system. Whereas over here, there are a variety of different ways to abstract and logically separate those systems. And throughout the course, we're going to talk about a bunch of different virtualization concepts. But the core feature is that this physical infrastructure could be logically separated to support potentially multiple operating systems running simultaneously on that shared infrastructure. And then even top of a single operating system, you could even have multiple applications that are kind of each running in its own little mini virtualized environment so that they don't in fact coexist with other applications. They have their own logically separated environment to run inside of. And if you're already familiar, this is actually containerization, but that's a subconcept of virtualization that we'll get into throughout the course. Moving on, we have storage and databases. There's two key concepts around storage to first understand. And again, these concepts are not necessarily unique to cloud computing, but they're going to be important to understand for how cloud computing is enabled. The first one is network attached storage, or NAS. And this is a concept of taking a single hard disk or solid state drive, whatever the case may be. It's going to be taking a single disk and making it network accessible to multiple systems over TCP IP. And this provides file level access. So some of you might be familiar with an organization that has perhaps a shared network drive that you can access and use to store shared files that you work on collaboratively, perhaps with your coworkers. And that's an example of a network attached storage. On the flip side of this, there's another concept called storage area network, or SAN. And that's the concept of taking multiple disks and then logically viewing them as a single disk to a system. So that's what you can see down here, that it appears as a single disk to the system. And the advantage of this is that if you have multiple, let's say 10 gigabyte drives, then this would be viewable to your system as one 30 gigabyte drive, as opposed to three 10 gigabyte drives. And because of this, the system is using block level storage to access these devices. And that allows it to store, read and write different files on these drives. And those files might actually be stored partially on multiple drives. Okay, so taking these concepts and then thinking about it in the cloud, we'll talk about databases specifically. In this on-premises environment, you have the hardware and storage, and then on top of that, you have the operating system. And then on top of that, you might have the database, and then within that, you have the data. And all of this is going to be customer managed in on-premises environments. Whereas when you shift into the cloud, some of the responsibility of managing these things is going to shift into the cloud service provider's responsibility. So of course, starting at the bottom, you have the hardware and storage, which is going to be managed by the cloud service provider. The operating system would be managed by the cloud service provider. And then really specifically, when we're talking about managed database services, the database itself is going to be managed by the cloud service provider. So as an example, that would be Amazon Web Services relational database service. And they're going to manage the SQL database or whatever the version of database you're using. But something really important to consider, to remember here, is that the data will always be customer managed. So even if the database in RDS inside of AWS is managed by the cloud service provider, the data is still going to be customer managed. Last slide, we're going to be talking about networking and orchestration. And the reason we're discussing this is to help you understand that the capabilities that the cloud has to interconnect resources and automate cloud workflows is what enables customers to build geographically distributed and highly efficient workflows in the cloud. So specifically, cloud service providers are going to have global infrastructure that ensure low latency between these different geographical locations, and then a high bandwidth to make sure that customers are able to continuously transmit high levels of data between these different data locations. And then, of course, it needs to be reliable to ensure that there is no loss of data between those locations. And then because these global infrastructures can become very complex to manage, there are some key concepts that we'll discuss throughout the course that are going to be essential for allowing the cloud service customer to manage this complexity. And that's going to be infrastructure as code, as well as auto scaling and the automation of workflows within the cloud. Okay, in summary, we talked about some core concepts such as virtualization, some key definitions of different types of storage and databases and how that translates into the cloud. And then finally, some key networking and orchestration concepts that allow both cloud service customers and cloud service providers to enable highly efficient global workflows. Welcome to this lesson on cloud activities, service capabilities and categories, and deployment models. So as promised in one of the previous lessons, in this lesson, we are going to dive a little bit deeper into some concepts like cloud service capabilities and deployment models. Prior to that, though, we're going to quickly talk about some activities that different stakeholders might take in the cloud. So diving into this, we have this cloud service activities concept, and within it, we have consumer, provider, auditor, broker, and carrier. And you might notice that these are fairly similar to the different roles and responsibilities that we had previously discussed in the cloud. In this case, these are concepts that ISC Squared really wants you to understand as far as different activities that the different stakeholders might take in the cloud, and that it's not necessarily a one-to-one mapping to the roles. So a cloud service customer might consume, but a cloud service customer might also audit or broker and that kind of thing. So these cloud computing activities are distinct activities that shape how service delivery and oversight is taking place. Similarly, we have these cloud service capabilities, and where the different service models are kind of a customer-facing concept, such as IaaS, PaaS, and SaaS, you notice these are very similar to those concepts. But in this case, you should step into the role for a moment of cloud service provider. And these are capabilities as a provider that you should be concerned about providing to your customers. So for application, you should be able to deliver software applications over the internet for your customer. And then for platform, you want to be able to provide tools and environments for developing, testing, and deploying applications. So you might be talking about CI/CD pipelines in this case. If you're not familiar with that concept, that's okay. We'll get into that later. And then finally, we have infrastructure, which is offering raw computing resources such as storage, compute power, and networking. In this, we're talking about a lot more than just CPU and RAM. We're talking about being able to configure networking and access storage devices that are separated from your other components for infrastructure. Again, switching back over to the customer role, we're going to go back into the actual service models, which are IaaS, PaaS, and SaaS. And if you remember from the first time we discussed it, that on this end of the spectrum, we have much more customization, but as a customer, you also have much more responsibility in configuring the security and operability of IaaS services. Whereas on this end, we have much more convenience, and it might be quicker to go from initial deployment to functionality for your services, but they're also going to lose out on some ability to create highly customized configurations. Okay, so specifically for IaaS, we are accessing computing resources online without actually physically owning the hardware. And that's the core concept behind what IaaS is. Some really good examples of this are going to be AWS's EC2, Azure Virtual Machines or VMs, and then finally Google Compute Engine. Next up, we have Platform as a Service or PaaS, and this is where the cloud service provider is providing an opportunity for customers to develop, run, and manage apps without handling the underlying infrastructure. So for examples, we have AWS Lambda, Azure App Service, and Google App Engine. Okay, and then finally, we'll talk about Software as a Service or SaaS, and this is where cloud service providers are giving customers the opportunity to use applications online anytime and bypassing software installations. So what that means is that the cloud service customer does not have to install their service or their application before being able to use it. That step is essentially already done, and the cloud service provider is providing that front end to essentially just get straight into using the service and the application. So some really great examples of this that you're probably already familiar with, at least some of these, are Dropbox, Zoom, Slack, Trello, and Shopify. All of these are SaaS applications that are hosted on a variety of different cloud service provider environments, and you as the customer get to just start using those applications right away. Jumping into cloud deployment models, we're going to discuss in a little bit more depth as to what these are, but as a quick recap, we have public, private, community, multi-cloud, and hybrid. So public cloud is when services are available to the general public. And again, this is also a multi-tenant environment. So the CSP is going to be responsible for logically separating customers. But as a customer in a public cloud, you will likely be sharing physical infrastructure with other customers, but there will be a strong logical separation between your workloads and theirs. In a private cloud environment, however, there is hardware that is dedicated to a single customer. That doesn't mean that the customer manages that hardware. The CSP is still managing that hardware in a centralized data center, which is why it's still resource pooling, but it is not multi-tenant. So you as a tenant in this case have dedicated hardware. As you can imagine, typically private cloud infrastructure is much more expensive, but in certain highly regulated industries, it might be critical to maintaining compliance. Next up, we have community cloud, and that's sort of a pseudo private cloud, but the specific concept behind community cloud is that it's hardware dedicated to a group of customers with common interests. So for example here, you imagine a series of different hospitals all have very similar hardware requirements for what they have to meet in their IT infrastructure to maintain compliance. And because these customers all have very similar requirements, or if not the same requirements, the cloud service provider can have hardware dedicated to customers with those requirements to ensure that they are able to meet them without necessarily having to pay for the expense of a private cloud. But in this case, it is multi-tenant, but the other tenants in that environment are groups with the same types of interests, for example, hospitals or schools. And then I'm going to skip down here to multi-cloud, which is where a customer is using services from multiple CSPs. So an example of this is going to be an environment where you have some services running in Amazon Web Services, and then maybe some others in Microsoft Azure, and maybe in some cases those are even interconnected. But at the end of the day, an organization has services running in multiple different cloud service providers, and it's critical for them to find ways to centrally manage and understand all of their cloud resources across their multi-cloud environment. And then finally, we have hybrid, which again, I think is pretty intuitive here, but it's just a combination of two or more of the other deployment models and or on-premises. So you might only be public cloud and on-prem. That is still considered to be a hybrid deployment. But if you have some public infrastructure and some private infrastructure, but no on-premises infrastructure, that is also still a hybrid deployment. Okay, in summary, we talked about the different activities that people might take inside of a cloud service environment, the capabilities that a cloud service provider should be providing, as well as specific definitions of the different service categories and deployment models in the cloud. Thanks for watching. I will see you in the next lesson. Welcome to this lesson on cloud shared considerations. In this lesson, there are 4 key learning objectives. The first one is some key terminology that we'll use to set the stage for future lessons. Next up, we'll talk a little bit about security and privacy, which are probably terms you're already familiar with, but we're going to dive a little bit into how they affect cloud specifically. Next up, we'll talk about some governance and compliance topics, and then finally some service management. So getting into it, starting with terminology, the first term we're going to go over is interoperability. This is a system's ability to integrate and communicate with other diverse systems. So most modern applications today communicate using something called APIs, or application programming interfaces. And that's essentially an application's way of sending and receiving data from other systems. So the more interactive a system or an application is able to be with other applications, the more interoperable it is. Next up, we have portability, and this is the ability of a system or an application to be transferred both between CSPs and even back and forth between the cloud and on-premises systems without significant disruption to the application's ability to operate. Next up, we have reversibility, which is similar to portability, but very specifically focusing on the ability of an application or system to move from the cloud back to on-premises without disruption. Next up, we have availability, which is a term you might already be familiar with, but in this case, the CCSP exam guide specifically wants you to understand availability as being a CSP's responsibility to ensure reliable access to infrastructure, which is typically outlined in something called a service level agreement or an SLA. Next up, we have resiliency, which once again, common term, but in this case, you should specifically focus on it as being a CSP's ability to enable business continuity and disaster recovery. And this is especially capable with CSPs that have multiple regions and zones that are geographically dispersed, which maximize an organization's ability to create robust infrastructure. Next up is performance, and in most cases, major CSPs have pretty high performance because they have a lot of excess capacity and redundancy built into their systems. However, there are certain limitations such as network issues that influence this design because ultimately, there are many scenarios in which cloud customers are still traversing public infrastructure that is managed by major telecom companies that is going to have a finite amount of bandwidth that you can send through those networks. Finally, we have maintenance and versioning, and this is the process of updating, patching, and managing the software versions of systems and software running inside the cloud environment. And the responsible party for updating the systems does vary based on the service. So thinking back to the shared responsibility model, in some cases, it's either this cloud service providers or even the cloud service customer's responsibility to update and patch those software solutions. Moving on to security and privacy. Once again, these are probably terms you're familiar with, security being the protection against unauthorized access and privacy being safeguarding users' personal data and information. However, specifically when it comes to the cloud, it's important to understand how to identify where your data is when using a CSP. CSPs make significant efforts to make their environments secure, but at the end of the day, the data security is always the customer's responsibility. Complex cloud solutions also make the cloud much more susceptible to security issues such as misconfigurations, which is one of the common vulnerabilities that we see in the OWASP top 10. When it comes to privacy, the involvement of third-party providers is always going to be complex. Some important terms that we'll go over throughout the course are going to be related to the GDPR regulation, which are terms like data owner, custodian, and subject that are all going to be related to privacy. Okay, jumping into governance and compliance. These are some key terms that will be important to understand for the exam. The first one is that governance is specifically relating to the development and enforcement of policies, procedures, controls, and oversight of a cloud environment. Next up, we have regulation or regulatory compliance, which is a requirement to adhere to both federal and contractual regulations. So you might be familiar with HIPAA, GLBA, or SOX requirements, all of which we will go over later in the course. But regulation also covers contractual requirements where organizations are required to adhere to agreements that they have made with other organizations. Finally, we have auditability. And this is the concept of ensuring that a CSP meets security standards via external evaluations. So some common ones you might hear of are going to be SOC or FedRAMP. In fact, most major, if not all major, CSPs should have a SOC 3 report published for public consumption to ensure that the CSP itself is meeting certain requirements. Finally, we have service management. And the first term to go over in this category is going to be the service level agreement or SLA. And this is referring to a contract between organizations where you establish a required performance metric of a solution or a service provided. So ones that you might be familiar with hearing are going to be availability. So you might have a requirement of, let's say, 99% availability of a SaaS application. And in the event that this SLA requirement is not met, then either the service provider of that SaaS application would owe some damages to the organization that was impacted by that loss of availability, or in some cases, the customer of that service provider may be within their rights to terminate a contract. And then finally, we have the concept of outsourcing, which once again is not a term that's unique to the cloud, but in this case, we're talking about contracting with an external party to provide a system or service. However, there are certainly complications when it comes to compliance in the cloud because there may be certain regulatory requirements that require customer data is only handled within certain geographical locations, such as a country. So when it comes to outsourcing in the cloud, it's certainly important to consider the advantages and risks of outsourcing when developing business strategies. In this lesson, we talked about some key terminology that will be important for the CCSP exam. Following that, we talked about some additional terminology in the categories of security and privacy, governance and compliance, and finally, service management. Thanks for watching. I'll see you in the next lesson. Welcome to this lesson on impact of related technologies. In this lesson, we have 5 learning objectives. The first of which is talking about data-driven technologies, decentralized and secure computing, connected world and real-time processing, modern infrastructure and deployment, and finally, future of computing. Getting into data-driven technologies. This is technologies that will allow us to transform raw data into actionable insights. Specifically, when we're talking about the cloud, data science is going to be both enabled and benefit from the cloud because it enables us to parse large data sets to detect anomalies. Leveling up a little bit from that, we have the concept of machine learning, which is a system's ability to self-improve, which in the cloud could enable us to make security and privacy concerns through machine learning-powered decision-making. And then finally, we have artificial intelligence, which is a little bit of a step above machine learning, and it allows us to harness computational power to mimic human intelligence. Next up, we'll talk about decentralized and secure computing. This allows us to enhance trust through decentralization and encryption. First concept here is going to be confidential computing, which is the idea of using cryptography to protect data during processing. And it uses a trusted environment to ensure authorized access only. It's also going to integrate well with other concepts such as edge computing, which allows us to support distributed workloads. And then we have blockchain, which is an open distributed ledger of permanent verifiable transactions. So using this icon a little bit, we can use each of these small blocks to describe a block on the chain. And the idea is with blockchains that each block contains a hash of the transaction that occurred in the previous block, or in some cases, maybe a series of transactions, which means that there is a verifiable method to track each transaction or set of transactions in the chain. There are a variety of different solutions that the blockchain technology supports, and it especially helps us ensure data integrity across multiple servers or CSPs. However, there is the potential of vendor lock-in, which essentially means if you pick a specific blockchain to build your technology on top of, then it may be that other CSPs don't necessarily support that blockchain, in which case you would be locked into using the vendor that you initially started building in. All right, now we have connected world and real-time processing. The first concept here is the Internet of Things. And the Internet of Things is a very broad set of services and devices that support a multitude of different capabilities that you are probably already experiencing. So some common ones that you might be familiar with are going to be smartwatches, internet-connected recording devices, or even things like smart thermostats inside of your home. Typically, anything outside of cell phone or computer is going to be in this sort of catch-all category of Internet of Things. And certainly there is a strong capability in the cloud to store vast amount of IoT data, which is helpful because many IoT devices have limited storage, but persistent connectivity. That being said, there are certainly security concerns when it comes to IoT devices. Many devices lack robust security, and with the limited amount of computing power that are on some devices, there are limitations as to what security can even be implemented. A significant role that the cloud can play to address this problem is centralizing the monitoring and control of these end devices. Beyond that, in this category, we have edge computing. The concept of edge computing is geographically or logically dispersing the location on which certain computing and processing requirements are taking place. So if you see one of these end user devices right here, instead of this end user device just passing traffic through this device, or maybe this edge location that we see here for ultimately some processing to occur in some centralized location, the cloud enables us more so than ever to distribute the ability of these systems to make decisions and process data at edge locations, which can help reduce latency for customers. So for example here, many cloud service providers allow us to cache certain static content or even make some dynamic decisions for how to deliver content to an end user at these edge locations, which means that when an end user browses to, let's say, a website, their system doesn't necessarily need to communicate all the way back to some centralized server. It's going to be able to get most, if not all of the data it needs from a location that is significantly closer geographically to their current location. One of the security challenges with edge computing is the limitation of traditional security controls, as well as issues with physical access, data integrity, and transit interception. All right, now let's talk about modern infrastructure and development. If you remember, we talked about virtualization, and a subconcept of virtualization is going to be containerization. So a container is the abstraction of an operating system to an application. So in this case, over here, we have maybe a small example of an on-premises environment where on top of a physical infrastructure, we have a single operating system. And then on top of that single operating system, we have a handful of applications that share an execution environment. With containerization, not only can we have multiple potential operating systems, with containerization, we can isolate these applications in an environment where it's not going to be logically co-located with other applications. And this makes these applications much more lightweight, efficient, and portable. Some common containerization technologies that you should be familiar with are going to be Docker and Kubernetes. So the terminology here is a Docker container is going to be one of these little runtime environments. And then a Kubernetes cluster is more about the orchestration of multiple containers within a cluster. All right, next up we have modern infrastructure and development. And the most important term here to understand for the exam is going to be this DevSecOps concept. And this term is actually an amalgamation of the terms development, security, and operations. And the idea is that rather than having a specific phase where development takes place and then security conducts testing and then operations uses applications or maybe deploys applications, we are integrating teams that work in these domains to make sure that we're more quickly integrating feedback into the development process to reduce the amount of time it takes to not just release application updates, but release secure and needed application updates. Further on this concept, you might hear the term shift left security. And the idea is that we are considering security earlier in the process of development when compared to normal development cycles. So this over here is an example of what a DevSecOps development cycle might look like. And you'll notice here that this is continuous. So the idea is that as you work through these phases, there's always a process for you to circle back around and continue to code and build and test your application code. It's not necessary for you to memorize these steps, but it is useful to be familiar with what this process looks like for the exam. Okay, and finally, we have the future of computing. And specifically here, we're going to talk about something called quantum computing. And this is a complex topic that we won't necessarily get into the details of how it works. But the idea is that quantum computing makes a computer much better at solving complex problems much faster, but it isn't necessarily much better at solving easy problems any faster than existing computers. So the reason that's important is because the current design of encryption algorithms means that encrypting data is computationally easier than decrypting data. And that makes it so that it's difficult for a current day computer to brute force the cracking of the encryption keys to reveal the contents of the data without using the key. If you have the key, it's not overwhelmingly burdensome for a computer, but if you don't have the key, it's very difficult to brute force the decryption of that data. However, there's another concept that you should be familiar with called hashing, which is a one-way encryption, which is computationally relatively easy in most cases, depends on the exact hashing algorithm that you're talking about. So again, an important thing to understand with quantum computing is that it creates vulnerabilities in current day encryption algorithms where quantum computers could potentially be much more effective than current computers at cracking complex problems such as encryptions algorithms. However, it's not necessarily going to be any faster at solving simple problems. Certainly there are other applications of quantum computing such as boosting AI and ML technologies, but in this context we should be concerned about its ability to render current encryption algorithms potentially as obsolete. There have been recent advancements in the development of what's called quantum resistant encryption algorithms, and in the next few years we may see increased usage of those types of technologies. In summary, in this lesson, we talked a little bit about a variety of technologies that help enable the possibility of cloud operations and are certainly important to consider when it comes to both maximizing our usage of the cloud as well as interacting with existing technologies. Thanks for watching. I will see you in the next lesson. Welcome to this lesson on cryptography and key management. In this lesson, we're first going to talk about some cryptographic challenges that you can face in the cloud, and in direct relation to that, we'll talk about some key management solutions. So getting into it, we have three main cryptographic challenges that we should be concerned about in the cloud. They're all pretty much related to making sure that data is encrypted both in motion and at rest. The first problem is that regardless of what cloud infrastructure you have deployed, traffic between external users and the cloud is something we need to be concerned about protecting, because in many cases, this traffic is going to be traversing untrusted networks. Next up is this concept of multi-tenancy, which we discussed a little bit, but in this case, as a customer of the cloud, one of the best ways you can protect yourself in a multi-tenant environment is to make sure that all of your data and systems are encrypted using well-managed keys. And then finally, another complication of being in the cloud is that as a customer, you do not have access to the physical hardware. This includes hard disks. And so unlike on-premises infrastructure, there is no way to absolutely validate that there has been physical destruction of hard drives where you're storing sensitive data. The solution to all of these is going to be cryptography and the application of encryption using cryptographic keys. So now we'll talk about how to manage those keys. There are three key activities when it comes to key management, and that's the generation of the key material, how you store the key, and then how you manage the key. This is typically referring to both user and system access to the key, using it to encrypt and decrypt material, as well as how we are destroying the key at the end of its lifecycle. So over here we see three key services that are in use in our three most popular cloud service providers, and these services directly support these activities when it comes to key management. So in AWS we have KMS, which stands for Key Management Service, and then in Azure we have a Key Vault, and then finally in GCP we have Cloud KMS. A couple of key takeaways when it comes to key management solutions is making sure that we're keeping our keys away from the data that was used to encrypt. In some cases, depending on regulatory requirements or even just organizational policy, you may even keep keys outside of the cloud environment where most of your infrastructure is deployed. And the benefit of this is ensuring that if there's a compromise of your cloud systems, that is less likely that those adversaries will also have access to the solution where you are storing your keys. This becomes additionally complicated when you're talking about multi-cloud environments. If you have infrastructure deployed into multiple cloud environments, the infrastructure and those systems all need access to a similar set of keys or even just a single key. It is exceedingly complicated to set up access and permissions. In some cases like that, it may also even be beneficial to use third-party key storage organizations which provide more simplistic management of your keys. All right, that wraps up this lesson. And in summary, we talked a little bit about some encryption challenges that you might face in the cloud, as well as touching on the primary solution to some of those challenges, which is going to be cryptography and managing the keys that we're using in our cryptography. Thanks for joining. I will see you in the next lesson. Welcome back to this lesson on identity and access control. In this lesson, we're going to be talking about 4 different types of access, and that is physical access, user access, privilege access, and finally service access. So to begin to physical access, this is pretty straightforward, and it's just referring to actual physical access to data centers and servers. And really all you need to understand is that if it's a CSP-owned facility, then the CSP is responsible for maintaining control over the physical access to the systems and data center in general. Whereas when it's a customer facility, it is of course the customer's responsibility to maintain that access. In this case, it might be referring to a hybrid cloud deployment where a customer has some on-premises systems that perhaps have configured access to the cloud systems. And of course, it's going to be the customer's responsibility to secure the physical access to those systems. In other cases, there are some rare scenarios where a customer may have physical devices that they are essentially renting from a cloud service provider for a variety of purposes. In those cases, the customer is also going to be responsible for ensuring the physical security of those devices, even though they are owned by the cloud service provider. Next up, we have user access. And there are some key questions to ask when it comes to user access, such as who can access data or systems, and then how are we logging and monitoring that access? And then how and when are we reviewing that access to ensure that it is not more than is required, or in some cases may not be enough. There are 2 key types of controls we can use to enforce this, which are administrative access controls, which is typically referring to policies and procedures. So think about essentially the rules that your organization has around how users are able to access systems, as well as technical access controls, which is the systems that are actually enforcing policies that we have set forth. Another concept I want to touch on briefly here is the idea of federation or identity federation. How this works is that there's a trusted third party here who can authenticate users. So this user would work through this identity federation service to validate its identity, and then applications such as email would trust this third party when it asserts that this user has been authenticated. This technology enables us to have things that you might be familiar with, such as single sign-on. Okay, next we have privileged access. And this type of access can coincide with other types of access, even physical access, such as a physical data center, which might have certain areas that only authorized employees are allowed. That's a type of privileged access. There's also a key term within privileged access, which is privileged access management, or PAM, which is a term you should be familiar with for the exam. Within logical systems, privileged access is usually referring to administrative accounts. Within our 3 main cloud service providers, we have services like AWS IAM, Azure AD, and GCP IAM that helps us both manage identity and privilege within our cloud environments. Of course, IAM stands for Identity and Access Management, and AD stands for Active Directory. In order to make sure that we're meeting security standards when it comes to privilege access, you should apply the principle of least privilege, meaning we only give the absolute minimum necessary permissions in order for people or systems to complete the work that they need, as well as maintaining our general baseline cyber hygiene, such as using multi-factor authentication, strong passwords, and most importantly, having separate accounts for administrative versus non-administrative actions. So if a user needs to have an administrative account, they should also have a regular user account for their day-to-day operations, and they should only be using their administrative account when it's absolutely necessary. Okay, next up we have service access. And compared to the others, I think this one has maybe a slightly less intuitive name. Specifically for the purposes of the exam, you should understand service access to be referring to the idea that technically CSP admins can access systems and data that belong to the customer. And while most major cloud service providers have strong controls over when and how that can happen, or preventing it entirely, it is still technically a possibility. The best solution to this is for the customer to just encrypt their data and securely control the keys which was used to encrypt their data, which makes it so that if the CSP admin does affect these systems, that all of the data that they're touching is encrypted and therefore effectively inaccessible. All right, in summary, we talked about 4 different types of access and specifically how they pertain to the cloud. The first one is physical access, and then we have user access, privilege access, which once again can sometimes overlap with these other types of access. And then finally, service access, which is talking about a CSP's ability to affect the physical systems that are being used by the customer. Thanks for joining. I'll see you in the next lesson. Welcome back to this lesson on data and media sanitization. In this lesson, we're really going to continue to drive home the importance of cryptography and key management in the cloud. We're specifically going to talk about a concept called overwriting, and then following that, we'll talk about another term called cryptographic erasure, or in other words, crypto shredding. So overwriting, once again, is not a concept that's unique to the cloud. This happens even on your everyday systems at home, where when you delete a file, over time, eventually that file is overwritten. But until it's overwritten, that data still exists on your disk. The only thing that happens is that your disk just forgets where that data is stored, which tells your operating system that it's no longer accessible, but the data is still written to the disk until it's overwritten. This overwriting just happens naturally over time, but it can be very unpredictable. And so in this case, if we imagine here that our data is these pink disks that we want to protect, then as time moves on, we can see that the disks with our sensitive data are eventually overwritten with new data, effectively erasing the data that we want to protect. However, that obviously creates risk when it comes to the undetermined amount of time that our data is still written to those disks, but those disks are no longer in our control as a cloud customer. So in order to mitigate this risk, we can back up a little bit here and apply encryption to our sensitive data on these pink disks, which means that even as it takes time for these disks to be overwritten, it doesn't matter because the data that we want to protect is effectively gibberish to anybody that's accessing it without these keys. In order to more effectively protect these keys, we have this concept of cryptographic erasure, which allows us to make data unreadable through key destruction. So initially, if we are encrypting our data at rest using these keys, then if we destroy these keys in one way or another, then that data that we encrypted becomes entirely unreadable and therefore secure from anybody that we perhaps wouldn't want viewing that data. So this concept is referred to as cryptographic erasure or crypto shredding. And there's a couple different ways that you can destroy these keys. If you're maintaining these keys on systems that you have physical access to, such as on premises, the easiest method is to physically destroy the disk where the key material is held. However, in the cloud, obviously, we've discussed that that's not always a possibility, if ever. And so another mechanism you can use is to instead encrypt the key material within the environment using a key in an environment that you do control, and then subsequently destroy the key that you do have access to, which renders the key material in the environment that you do not have access to gibberish and therefore unusable. It's a little bit convoluted, but the idea is that rather than having to reliably erase the bits and bytes that are written to a disk on a system within a cloud service provider, you just have to destroy the material that was used to encrypt that data, and then your data is secure. All right, in this lesson, we talked about two concepts that are really important when it comes to cryptography in the cloud, which are overwriting and crypto shredding, or otherwise known as cryptographic erasure. Thanks for joining. I'll see you in the next lesson. Welcome back to this lesson on network security. In this lesson, we're first going to talk about some network security challenges, and then we'll talk about a few tools that might help solve some of those challenges. And then we're also going to talk about some networking related concepts such as zero trust architecture, as well as traffic inspection, geofencing, and monitoring. Some of the most common network security challenges we're going to face within a cloud environment takes us back to those 5 key features of what makes cloud computing according to NIST. One of those is broad network access. And if you remember, that's essentially the concept that cloud systems should be widely accessible to a customer using a variety of different protocols, which can be beneficial, but that also creates some additional risk in how we control that broad network access and can certainly lead to some exposure of those resources. More along that same concept, in the cloud, not only do you have exposure that you face in the traditional sense, which is systems exposed to the internet, which are potentially facing attack, identity and access management control is also critical for limiting exposure. Imagine now you have a set of cloud credentials, such as access keys, that could potentially be exposed, which means that we need to put special attention into how we're managing those credentials. With cloud infrastructure, there's also a much higher chance of traffic between a cloud service customer and a cloud service provider traversing the open internet or otherwise untrusted networks. And because of this, it is possible that bad actors could intercept that traffic and potentially lead to unauthorized access to sensitive data. And if you can guess, the most effective solution to this particular challenge is, of course, going to be encrypting your data in transit. Finally, we have the complex topic of building robust and secure network infrastructure in the cloud and rethinking how we design that architecture to include VPNs, virtual firewalls, and other common network security concepts. Okay, so diving into some tools now, the first thing we'll talk about is network security groups, or NSGs. And this is a broad term that refers to the ability in the cloud to micro-segment our applications. And ideally, within cloud infrastructure, you should take advantage of this capability to micro-segment as much as possible. More along those lines, the cloud allows us to apply virtual firewalls at each of those layers of this micro-segmentation, such as at the VM level, at the NIC level, or network interface card, or even the subnet level, which contains multiple systems, which allows us, of course, to create some layered defenses. VPNs can be a good solution to connect on-premises systems into the cloud securely to ensure that the traffic in between our on-premises systems and the cloud remain secure. And specifically for SaaS applications, the network exposure largely becomes the responsibility of the service provider of that SaaS application to manage, so that can be another effective method for reducing overall network exposure in the cloud. Next up, we have zero trust architecture, which is a concept that is commonly confused with the idea of principle of least privilege. The principle of least privilege is the idea that systems and people should only have the absolute minimum access and permissions that they need into the environment in order to complete their tasks and nothing else. However, zero trust architecture is the idea of creating a layered defense by requiring continuous authentication and authorization each time a person or a system requests a new level of access to sensitive data. So in traditional architecture, we might have a really well-defined perimeter, but essentially once you get inside this fortress, everything inside is trusted. And so we might find that people or even systems are maybe wandering into rooms we don't want them in, right? So if someone does get in, a better method here is to implement a zero trust architecture where we walk along this path, and each time we come to a critical point in our access to increasingly sensitive systems, there's going to be a mechanism that's going to verify the authentication and authorization for that level of access. This allows us to create an incredibly granular level of access control. To learn a little bit more about how zero trust architecture can be applied, there is some additional material in the NIST SP 800-207 documentation. Okay, finally, we have traffic inspection, geofencing, and monitoring. The first thing we should talk about is the difference between ingress and egress traffic. Ingress traffic is traffic that begins from either the internet or maybe just some sort of external network and is communicating with an internal system here, whereas egress traffic is the exact inverse of that, which is an internal system that is sending data out to some sort of external system or the internet. When designing inspection architecture, it's super important to consider including both of these directions of traffic in your inspection architecture, which are sometimes referred to as north-south traffic flow. Two common ways that we can capture this traffic is going to be through flow logs and then full packet capture. So flow logs is going to be a high level of information about the traffic that traversed a network. So think of this as being the who and the when, where a full packet capture is going to be the process of duplicating all communications between systems, which is going to fill in the gaps a little bit with things like where and what and why. That being said, full packet capture can be incredibly high volume to capture. And so in some cases, you can imagine that if we have gigabytes or terabytes or even petabytes of data transferring through a network, it becomes near impossible to complete a full packet capture, in which case we might have to default to flow logs and use different techniques to detect anomalies in that traffic flow. If you do want to capture full packet capture, however, it's not something that traditionally exists within the cloud, but there are services within our common cloud service providers that can enable this capture, specifically AWS VPC traffic mirroring, Azure variable packet capture, as well as GCP packet mirroring. Okay, then finally we have geofencing, which allows us to draw a logical boundary over a geographical location, and then we limit access to our systems to that geographical region. And of course, this can help us improve security and identify anomalies, but you have to consider when and where this type of control is appropriate to implement. All right, in summary, we talked about some network security challenges, some tools that we might use to help address some of those challenges, and then finally, zero trust architecture and traffic inspection, geofencing, and monitoring. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on virtualization security. In this lesson, we're going to talk about 4 things, which are hypervisor security, container security, ephemeral computing, and then finally serverless technology. Before we really talk about hypervisor security, we should talk about the different types of hypervisors. When comparing to traditional infrastructure where we have a base layer of hardware, and then on top of that, there's one operating system, such as Apple's Macintosh, Linux, or Microsoft Windows. On top of that, we will have a variety of different kinds of applications that are going to run in a shared environment. In a type 1 hypervisor, or otherwise known as a bare metal hypervisor, we're going to have hardware, and directly on top of the hardware, we're going to have that hypervisor layer. So some common solutions for this type of hypervisor are going to be VMware's vSphere and Microsoft Hyper-V. On top of this hypervisor, we'll have one or more guest operating systems, which is an important terminology. And these guest operating systems will be logically separate from each other. In a type 2 or a hosted hypervisor, the bare metal hardware is going to have a host operating system on top of it that you use for normal usage. And then on top of that, you're going to have essentially what is one of these applications that can then host guest operating systems. So when you're on your system at home, this is most likely the type of hypervisor you're using to host a guest operating system. And some common applications for this are going to be VMware and VirtualBox. An important point to consider here for the exam is that this bare metal type 1 hypervisor is by far the most common type of hypervisor that you will find in the cloud. But generally speaking, attackers prefer to find a type 2 hosted hypervisor because there's a possibility that this host operating system would be vulnerable. So now let's talk. to talk about hypervisor security. With a type 1 hypervisor, the attacker is going to be generally focused on trying to get into one of these guest operating systems or the hypervisor itself. That being said, typically hypervisors are fairly secure, and especially with a type 1 hypervisor that is hosted in the cloud, the cloud service provider is responsible for securing this layer right here. If an attacker can attack the guest operating system, then it is possible that they could escape the guest operating system and get into that hypervisor layer, and that's an important concept called VM escape. If they can do that, then the hypervisor layer is essentially the highest level of privilege that they can achieve, and they can then use that to attack other potential guest operating systems that might be running on that system. But you can see that this is a little bit less likely. With a type 2 hypervisor, the two main attack points are going to be the guest operating system and then the host operating system. Especially with your daily, at-home workstations, the host operating system could very plausibly have some vulnerabilities that could allow an attacker to get in. And if they control the host operating system, certainly they're going to be able to pivot into the hypervisor. Same thing on this side, they can also attack the guest operating system, and that's not great. Obviously, we don't want them inside that guest operating system, but if they do attack that guest operating system, it's still equally as unlikely for them to be able to go down into this hypervisor layer, although technically possible, which again is VM escape. Some solutions to these are going to be some effective logging and monitoring of our systems, both at the host operating system level and hypervisor level, depending on which type of hypervisor we're using. And then, of course, securing the hypervisor, which again, in a cloud service provider, where the CSP is managing this hypervisor, it's going to be the CSP's responsibility to secure. And then we also want to limit network access to and from the hypervisor. The more protected this layer of either type of hypervisor is, the more protected, of course, the guest operating systems are running on top of it. And then finally, patching. If you want to learn more about hypervisor security in general, you can use the NIST SP 800 TAC 125A revision 1. Okay, getting into container security, there's a handful of common challenges when it comes to container security. And again, as a reminder, containers are going to be a type of virtualized environment that's going to be running within an operating system where applications can be logically isolated from others. So some of the most common challenges here are going to be misconfigurations, having insufficient or poorly managed identity and access management, and that's for both systems and people. And then, of course, software bugs in both the systems and software that's running within the container. And then finally, security of the host system. Once again, thinking back to our previous slide, if any layer of that stack is compromised, the layers above it are certainly at risk. Some solutions here are going to be education and training to help address things like misconfigurations and inadequate IAM. And then limiting the OS functionality is going to help us secure that host system, because the less that's running on that system, typically the less it is vulnerable. And then finally, using tools specifically designed for containers, both when it comes to building the containers as well as managing it and identifying possible vulnerabilities within the containers. Moving on to ephemeral computing. This is a type of computing where resources are created on demand and then they are terminated immediately after use. So in the cloud, this means you design some sort of requirement or workflow, and you use services that are specifically designed to be able to handle that workflow and then immediately terminate the computing resources. Some of the challenges we face with this type of ephemeral computing where it doesn't exist for a long period of time is that it's difficult to monitor using traditional tools, such as agents. There are sometimes fewer options for security controls, both administrative and technical controls surrounding those types of resources. Anti-malware implementation is often difficult, once again, because it's difficult to do things like install agents that are going to be able to monitor those systems. And then finally, brief existence, which to some extent is an advantage, but also makes it challenging to monitor for security purposes. Some solutions here are going to make sure that we're properly configuring the resources or using tools that are going to identify situations where the configuration may not be ideal. And then secure definition files, which is the files we use to essentially define those requirements and tell the services that are running this ephemeral computing on our behalf how to complete the work. And then finally, we have crypto shredding, because the utilization of encryption is always going to be a viable solution to protecting our data in these types of environments. Okay, finally, we have serverless technology. And this is going to be similar to ephemeral computing, but in this case, we're using services where the CSP is solely responsible for maintaining the servers and then ultimately exposing that computing capacity to customers. Once again, some challenges here are going to be no traditional monitoring capabilities. You can't exactly install a monitoring agent when you're spinning up a temporary function. So one of the most important ways to secure serverless technology becomes securing those API endpoints, which exposes that serverless technology to some other network. In order to secure these APIs, we can use something like API keys, as well as, once again, making sure that we're properly configuring the security of the systems as much as possible and using tools and services that are going to help us identify where we may not have sufficient configuration. Okay, in summary, in this lesson, we covered hypervisor security and talked about the different types of hypervisors, container security, including some methods to help secure our containers, and then finally, ephemeral and serverless security. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on common threats. In this lesson, we're going to go over 3 common threat and vulnerability frameworks, which are going to be the Cloud Security Alliance's Egregious 11, the OWASP Cloud Native Application Security Top 10, as well as the original OWASP Top 10. We're going to very briefly cover these topics. However, for the purposes of the exam, I highly recommend spending time studying the vulnerabilities in these lists, as it will come up in the exam. We will also be covering some of these frameworks multiple times throughout the course, which again is why we're going to be going through these fairly quickly. First off, we have the CSA Egregious 11, which is a list of the most common threats specifically to cloud applications from the perspective of CSA's research. Right away, you're going to see some threats here that are certainly significantly impactful to the cloud, but aren't necessarily unique to a cloud environment. For example, data breaches are certainly something that we can experience anywhere within the field of IT, similar to misconfigurations and inadequate change control, as well as other topics here like insider threat and account hijacking. At the bottom here, we have a URL, which will take you directly to these top threats to cloud computing built by the Cloud Security Alliance. Next up, we have the OWASP Cloud Native Top 10, which is going to be a list built by the Open Web Application Security Project organization, but specifically focusing on vulnerabilities that are targeting the cloud. We see some interesting ones here, such as this one highlighting the possibility of insecure cloud containers, which highlights the importance of some of the security solutions we went over in the previous lesson talking about container security. Once again, there's a URL at the bottom of the page here that you can use to further study these OWASP Cloud Native Top 10 for the CCSP exam. Finally, we have the OWASP Top 10, which is the original top 10 key vulnerabilities that OWASP has identified as affecting web applications. These applications are not specific to the cloud, but a web application can of course have the same vulnerabilities in the cloud as it would on premises, especially if it's running in a service like Azure Virtual Machines or AWS EC2. Some important vulnerabilities in this list are going to be cryptographic failures, which highlights the importance of effectively managing keys and cryptography in general in your cloud environment, as well as security misconfigurations, which is an incredibly common problem within cloud environments because globally, there's a big rush to migrate into the cloud, and there's still a problem within the industry where there is not always enough qualified individuals to help build and secure our workloads in the cloud. Once again, you can use this URL to access the original OWASP Top 10 and make sure you study these before going into your CCSP exam. In summary, we briefly introduced these three threat and vulnerability frameworks, such as the CSA Egregious 11, the OWASP Cloud Native Top 10, as well as the original OWASP Top 10. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on security hygiene. In this lesson, we're first going to talk about some basic security hygiene, and then after that, we'll talk about patching, baselining, and then how we can use patching and baselining together. So first off, we have basic security hygiene. And something important to point out with this is that the reason it's considered basic is because you should be doing some or even all of these practices to ensure we're meeting kind of a minimum standard for maintaining our security in our environments. So the first one is going to be continuous vulnerability scanning, so we can constantly be aware of what vulnerabilities actively exist within our environment so that we can start to develop either mitigation plans to contain those vulnerabilities or remediation plans to remove them entirely. On top of that, we should be maintaining and updating our asset inventories because knowing what types of assets we have in any environment, and especially in the cloud, is going to be an important step in knowing what and when we have to secure things. Next up is going to be regular penetration testing, which helps us identify and strengthen weaknesses or misconfigurations. However, this is an incredibly important one to consider that penetration testing should not be your only method for identifying vulnerabilities. It should only be one piece of the puzzle. And then finally, we have regular and secure data backups. Especially in today's day and age where ransomware is a common type of attack, especially in the cloud, having regular and secure data backups that are separately hosted to our infrastructure can help us recover from those type of attacks without having to engage with an attacker. Next up, we have patching. So patching is a practice of updating systems and software to the latest secure version. And regular software patching is incredibly critical. Something that's useful to understand is that many attackers in this industry will go for the low-hanging fruit, meaning people that have known vulnerabilities on their systems, and patching can be a way to remove those known vulnerabilities. Especially in environments where we can automate the installation of these patches, that's absolutely going to be a best practice. Depending on the exact service or the service model that you're using, and even depending on the CSP that you're working within, patching is going to be a responsibility of different parties. For example, with IaaS, the patching of the operating system is largely going to be responsibility of the customer. However, the CSP is going to do everything they can to help provide other services that are going to identify a need and automate the patching, but it is ultimately the customer's responsibility. Whereas with PaaS and SaaS offerings, the underlying platform and systems that support those services are going to become the responsibility of the CSP to maintain. Once again, the easiest way to understand that is if the customer can configure it, the customer should configure it. All right, now let's talk about baselining. Baselining is the practice of establishing a foundation of approved settings, which then allows systems and users to build and expand upon those baselines. So we see this icon of a foundation over here, and this baseline is going to be a strong foundation on which we can then build applications. In the cloud, it's a best practice to establish this baseline using infrastructure as code, or IAC. And if you do use IAC to build that baseline, then you can create something called immutable architecture. Immutable architecture is environments where that baseline is not editable after deployment, and that baseline is re-established when the environment is rebuilt, which removes any possibility of something called configuration drift, which is where we hit this concept, which is patching a future by rebuilding it instead of modifying existing infrastructure. And then finally, a good practice is going to be to audit the configurations of your current systems against the configurations that were established in your baseline to help identify situations where the infrastructure has once again drifted from this baseline. All right, finally, we can talk about combining the concepts of patching and baselining to create a secure environment. So in this example, we have a load balancer, and this load balancer is evenly distributing traffic between three systems right here. And traditionally, when we need to upgrade these systems, we might upgrade version 1 to version 2 on this system and then repeat the process from version 1 to version 2 on this system, and then once again repeat the process over here. By using baselining to create a new secure image for this system, instead of upgrading 3 times over, we can just get rid of these systems. Of course, not until we've built these ones, but we can use that new secure baseline to create the version 2 of the system and then just replicate it to replace each of the systems that we were originally using. And then now the load balancer is just going to start shifting traffic to the new version 2 of this system. So there's multiple benefits to this architecture. First, it reduces the time spent updating these systems by making it so you only have to do it once for each new version. And then on top of that, allows you to start with a good known baseline each time you create a system that is immutable once built. That means that in scenario 2, no one would be allowed to go and make changes to this version 2 system once it's created. And the only way to update it is to start with a new baseline and then update it to version 3 and then replace all of the instances that are running version 2. All right, in summary, in this lesson, we talked about basic security hygiene and the importance of capturing some or even all of these basic concepts, as well as patching, baselining, and using these 2 concepts together to create a secure infrastructure. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on the cloud secure data lifecycle. In this lesson, the only objective is to go over this lifecycle. Jumping into it, the cloud secure data lifecycle is made up of 6 independent steps, and these tend to be continuous in nature. For the purposes of the CCSP exam, I absolutely recommend memorizing these steps and some common activities that take place within them, as well as in the next module, we'll be going over some controls that we can use to help maintain security through each of these steps. But the exam is very likely to ask at least a few questions that are going to be related to the order or the activities that occur within these different phases. Right, so the first phase of the secure data lifecycle is phase 1, which is going to be the create phase, and this is where data is initially created. Something to consider here is that data isn't necessarily just referring to files that contain information. It could also be referring to system configurations and databases or even application code. Essentially, anything that we're writing to some sort of physical disk, whether it be in the cloud or even on premises, that's going to be considered data. So in this initial phase 1, we're creating that data. In phase 2, we are going to store that data on some sort of stored solution. So even in the cloud where the cloud service provider is managing that physical hardware, your data is still being stored somewhere on a physical system. In this phase, the most important thing is to ensure that we're saving our data securely and it is prepared for future retrieval and use. Next up, in phase 3, we are going to use that data. And this is specifically where systems and people might be accessing, viewing, or processing that data for a variety of different tasks. For example, if a file is uploaded into some cloud storage location, and then it kicks off a workload where another system takes that file and processes it in some way, and then generates some new modified version of that file to store somewhere else, that new modified version is going to start this process over where that workload created the file and then stored it in that secondary location for future use. Next up, we have phase 4, which is where we're sharing the data. In this phase, we might be granting data access to either other users or even other non-human entities such as systems or workloads. After that, we might archive the data. And archiving is essentially a way of storing data where it's not going to be regularly used, and it's meant for long-term purposes such as compliance or historical requirements. Finally, we have the destroy phase, which is going to be phase 6. In this phase, we're going to securely erase the data once we no longer need it. So let's say we've kept a piece of logging data for a certain amount of time that is required by compliance regulations, and we get to the point where we need to securely erase it. If you remember, as a cloud service customer, there is no way to physically access the drives on which our data is being stored within the cloud. So it's incredibly important to plan ahead for how you're going to securely erase this data using methods such as crypto sharding. All right, in summary, we talked about the 6 different phases of the cloud security data lifecycle, which you should take some time to memorize before going into your CCSP exam. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on business continuity and disaster recovery in the cloud. In this lesson, we're going to first talk about the difference between business continuity and disaster recovery. And then we'll talk about the cloud's role in resiliency and redundancy. And for the sake of clarity here, we're not talking about the cloud service provider. We are literally talking about the cloud cloud's role. And then finally, we'll talk about some drawbacks and considerations of using the cloud to support your BC and DR requirements. So the difference between business continuity and disaster recovery is that in both of these scenarios, some sort of disaster has occurred. So that could be a physical disaster such as a tornado, that has affected your data center, but it could also be some sort of cyber attack. Regardless, there's been some sort of event that affects the availability and the security of your systems. With a business continuity plan, we're specifically designing a plan that's going to allow us to maintain essential business functions during and immediately after a disaster. So when you think about a BCP, think about doing whatever we have to do to keep our systems running that maintain these business essential functions. Whereas a disaster recovery plan is the process that we go through to restore all services and operations to normal state after a disaster. So maybe there's a scenario where the BCP was unsuccessful in maintaining these essential business functions. The DRP is essentially that cutover where restoration practices take place. And even beyond that, if the BCP is successful in maintaining these essential business functions, the purpose of the disaster recovery plan is to restore all services and operations. So it may be that we're just focusing on those lesser priority systems that weren't necessarily maintained during the BCP phase. Okay, getting into the cloud's role in resiliency and redundancy, we should first define some nomenclature here to cover the different geographical regions that a cloud might provide. And as a little bit of a disclaimer here, most of our major cloud service providers are going to use the same nomenclature, but it may not be universal. However, these are still going to be useful terms for you to know going into your CCSP exam. So at the highest level, cloud service providers have something called regions, which is going to be a specific geographical region somewhere in the world where cloud services are offered. So in AWS, it might look something like US West 1, which is going to be this region over here. Or in Azure, it might look like West US, which might be generally capturing the western region of the US. These regions can be all over the world, and in some cases, there are multiple, either in the same country or even a section of a country. Within each of these regions, there are multiple availability zones, which is what we have over here. And these availability zones are a cluster of data centers. So in AWS, these availability zones are going to append some sort of indicator as to what availability zone you're talking about, such as US East 1, A or B. And then in Azure, it's going to be US East Zone 1 or Zone 2. And then once again, within each of these availability zones, you have multiple data centers. And this is the level where there is no naming convention, because as a cloud service customer, you don't have the ability to choose exactly what data center your systems or data is going to reside in. That is a level that is entirely controlled by the CSP. So at the highest level, we have regions. Within a region, we have multiple availability zones. And within an availability zone, we have multiple data centers. Okay, with that being said, let's talk a little bit about how the cloud can enable a customer to create resiliency and redundancy in the cloud. And largely, it's by using those geographically dispersed regions to make sure that our data and systems are backed up in multiple locations, or even operating concurrently from multiple geographical locations. This can support data and operations backup, as well as this redundancy of designing for failover without losing any availability. For example, if we have systems running in US East 1 and US West 1, and there's some sort of outage that causes a lack of availability to our US East 1 systems, if we have a load balancing setup that can automatically start pushing all of the traffic to that additional region, which in this case is US West 1, then the customers of our applications may be entirely unaware that we're experiencing some sort of outage. And then finally, in the cloud, we can also build systems that are serverless and containerized, which can help increase efficiency of continued operations. Some drawbacks and considerations to consider when building redundancy into the cloud is that there is going to be some additional cost of multi-region plans. If you're duplicating your infrastructure into multiple regions, the best thing you can do is find ways to efficiently scale those resources to make sure that despite the duplication, we're still effectively using all of the compute resources that we're paying for in the cloud. And then finally, another thing to consider here is that if you're using a cloud service provider to back up your assets, and that may be from another cloud service provider, or may even be that you're backing up your on-premises systems into the cloud is ultimately only going to be accessible through the internet. And so in the unlikely event that the cloud service provider has an outage, or if there is any sort of disruption in the network connectivity between you and the cloud service provider's nearest location, then it may become inaccessible to you because there's no way to physically access the drives on which our data is stored. Okay, in summary, in this lesson, we talked about the difference between a business continuity plan versus a disaster recovery plan, which is essentially maintaining critical systems versus recovering all systems. And then we talked about the cloud's role in enabling organizations to build secure, resilient, and redundant designs in the cloud. And then finally, we talked about a few challenges of using the cloud to enable our redundant infrastructure. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on business impact analysis, or BIA, and functional security requirements. In this lesson, as you might have guessed, we're going to talk about business impact analysis and functional security requirements. All right, jumping in, business impact analysis is largely going to be made up of 4 major steps. In this first step, we're going to identify assets that we need to be protecting, and then we're going to assess the impact of the potential loss of those assets. And then we're going to prioritize the effort that we're going to put into protecting and recovering those assets in the event of a loss. And then finally, we're going to build our plan for how to either reduce the likelihood of that event occurring or reduce the impact of that event. Some important terms to understand when it comes to business impact analysis are going to be a cost-benefit analysis as well as return on investment, or ROI. So a cost-benefit analysis is where we're going to weigh the pros and cons of different cloud solutions. And some benefits that we want to look for are going to be increasing resilience, ways to save cost that we're spending in the cloud, as well as maximizing uptime of our systems. So potential costs of this cost-benefit analysis that we should look out for are going to be loss of control of the underlying infrastructure and whether or not that is a good thing specifically for our business, as well as the risk of unauthorized access to our systems and outages. For return on investment, we're looking for a measurement of the value gained from an investment. And typically we want to find methods to capture an objective measurement as opposed to a subjective measurement. So specifically in the context of security, we're looking for ways to reduce risk, and then we're going to weigh that against the cost of security controls that we are purchasing to reduce that risk. And then we're going to decide what is our ROI based off of this cost and how much we're reducing risk. So some examples of this are increasing efficiency of our systems and applications, which could help potentially reduce cost or risk. And then of course, mitigating risks in the environment or even removing them entirely. And then finally, financial gains. Next up, we have functional security requirements. 2 really important concepts that we should remember for functional security requirements is going to be portability and interoperability. We've gone over these, but as a reminder, portability is the ability of systems to easily move between environments with minimal impact. So our systems and our applications can migrate either between on-premises and the cloud or between one CSP to another and continue to function as if nothing happened. So some challenges when creating portable applications is going to be that there are a wide variety of different tools and templates across the different CSPs. And the more we build our applications to maximize on the specific services offered by a CSP, the more we're risking something called vendor lock-in, which we'll discuss in a little bit. Some solutions to this are going to be using containerization services, such as Docker containers or Kubernetes clusters. And these are common technologies that all of our major cloud service providers are going to have robust support for. Another mitigation here is going to be to create seamless and automated movement between these environments. And this isn't necessarily easy to build, but could allow us to create more portable applications. The next term is interoperability. And this means a system's ability or system or application's ability to share data across various cloud and on-premises systems. So this basically means how well does your system or application communicate with other systems? So some challenges here in creating interoperable applications is going to be differences in security tools available in the different CSPs, as well as how we're building and enforcing our control sets within the cloud. Some potential solutions are using standardized APIs, which again, APIs is application programming interfaces, which are the building blocks of how systems and applications communicate with each other. And as well as using cloud brokers, which is a third party that can help us build effective communications between cloud service providers in a multi-cloud deployment model. As promised, we're also going to talk about vendor lock-in. Vendor lock-in is when you have built systems and applications that have a dependency on specific vendor features. So that means you've built an application that uses a service in a particular CSP where there is not an equitable service offered in other cloud service providers. And something important here is that in order to truly maximize the efficiency of our applications running in the cloud, vendor lock-in is not always an avoidable problem, and it may not be a problem at all. But when you're designing your applications, you need to consider what the risk is of building an application that puts you in a situation where you are unable to migrate your environment into other CSPs. Some challenges here are going to be financial costs, because if you're locked into a specific vendor and that vendor adjusts their pricing model, then you may be unable to migrate your environment without rebuilding and restructuring, as well as technical hurdles where the rebuilding and restructuring is perhaps not even possible. And then finally, early contract fees where you're trying to migrate out of a cloud and your infrastructure is well built to do that, but you have entered into a contract in which you might have to pay fees to terminate. Once again, some solutions here are going to be to build cloud agnostic technologies using technologies such as containerization like Docker and Kubernetes, and then putting a careful amount of attention into the design of your architecture and conducting that cost-benefit analysis to determine if a particular cloud service provider is the right solution for you. In summary, we talked about business impact analysis and the steps of a BIA, which are identifying assets, assessing the impact of a loss of that asset, prioritizing based on that assessed impact, and then finally planning around that prioritized list. And then we talked about a handful of functional security requirements such as portability, interoperability, and vendor lock-in. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on security considerations for the different service models and cloud design patterns. In this lesson, we're first going to do a review of the shared responsibility model. After that, we'll talk about security in the different deployment models such as SaaS, PaaS, and IaaS. And then finally, we'll talk about some cloud design patterns. So this is a summary of the shared responsibility model. And because this model is agnostic to the different cloud service providers, you might see some variants of this. But in this model, we can see that the cloud service provider is these big green dots, and the cloud service customer's responsibility is going to be these purple dots. So let's specifically get into how this applies to each service model. Starting with IaaS, we can see that data, identity and access, and application security are all going to be exclusively the responsibility of the customer, whereas network security and host infrastructure is going to be a mix depending on the exact service, or maybe even within a service, there's going to be specific configurations that might vary between the cloud service provider and the cloud service customer. And then at the very bottom here, we see the physical security, as always, is going to be the responsibility of the cloud service provider. Typically, within IaaS, the virtualization of resources is going to be the CSP's responsibility, whereas the operating system above is all going to be the customer's responsibility. A unique feature of this category is going to be the security of the CSP's network access. Next up, we have PaaS, or Platform as a Service. Once again, data is still the responsibility of our cloud service customer, but now we've seen this green push up in this model to where identity and access and application security are mixed. However, we can see that the cloud service provider's responsibility in these two categories is perhaps a little bit lesser than our cloud service customer. Everything below that, however, including network security, host infrastructure, and of course physical security, is all still going to be the responsibility of the cloud service provider. In this case, the underlying infrastructure is the CSP's responsibility, whereas app development and data is going to be the customer's responsibility. A unique feature of this one is middleware security, which is the specific platform on top of which our customer is building their application. And there's going to be some variability in this middleware configuration as to whose responsibility it is to secure it. And then it's highly dependent on the service and the cloud service provider. Finally, we have SaaS, or Software as a Service. And as always, data is still the responsibility of the customer. In this case, however, you can see that identity and access and application security become less of a responsibility of the customer. And again, if the customer has the ability to configure a setting, that typically means it is their responsibility to configure that setting securely. Most of the responsibility, however, in these configurations is going to be the SaaS provider. So everything from the infrastructure all the way up to the application is going to be the CSP's responsibility, whereas the data access and transfer from that application is going to be the customer's responsibility. In this case, the unique feature here is going to be the specific application of encryption and API controls, because this API is going to be how we're going to expose that SaaS application to external systems and users. All right, finally, we'll talk about some cloud design patterns. These are 3 different frameworks that you can use to help securely design your cloud infrastructure. The first one is going to be the SANS CIS control framework. And this control framework is specifically vendor agnostic, meaning it is not specialized to any specific CSP. And it's going to focus on your asset inventory and building security around your assets, as well as prioritizing the mitigation of risk. Next up, we have the well-architected framework, and this is going to specifically apply.
That's not from SANS. Why is she saying that's from the SANS sys control framework? That's the sys control framework. It's just, she's just getting it from SANS because they're hosting it on their site, but that's not, it's not their thing.
To a cloud service provider. So both AWS and Azure, as well as probably a handful of other cloud service providers, all have their own expressly designed, well-architected framework that has a variety of different pillars. And some common ones are going to be security pillar, reliability pillar, and the performance pillar. This is going to give you a framework to best design on a specific cloud service provider and not just in general. And then finally, we have the CSA enterprise architecture, which is another agnostic framework. But the focus in this case is going to be identity and access, as well as vulnerabilities and data protection. This framework is going to allow you to align your design to both IT and business requirements. Some key domains here are going to be ITOS, TSS, and security. All right, in summary, we talked about the shared responsibility model and how it applies to each service model. And then finally, we talked about some important cloud design patterns that we can use to securely design our infrastructure. Thanks for joining. I'll see you in the next lesson. Welcome to this lesson on DevOps security. This is going to be a relatively short lesson where we're just going to deep dive into DevOps security, otherwise known as DevSecOps. So diving in, the purpose of DevSecOps is to bridge the silos between different business units to make sure that we're more effectively providing feedback from each of these different phases of usage of applications into the development process. So you can see over here that the different phases of a DevSecOps cycle are meant to be continuous. But typically, you might start a project in this plan phase, and then after planning, you would write the code for the application, and then you would build the code to prepare it for deployment. And then after building, you're going to conduct a variety of different tests to ensure both security and functionality. And then you're going to release that build in order for it to deploy. And then finally, the system will be in operations, at which point you monitor your application. Once you're in that monitor phase, you may identify previously unknown vulnerabilities or perhaps new feature requests for something to add to that application, which is where you get pushed right back into this plan phase and you start the cycle over. The purpose of including both operations and security departments in this process is that we can identify those security requirements and potential vulnerabilities earlier in this process before we get to this deploy phase and the system goes into operation. Similarly, the operations team is typically going to be the people using the application, And if they have an opportunity to maybe slightly tweak or add features earlier in the process, such as when we're coding or testing, then it's going to reduce the amount of time it takes to both improve security and increase the efficacy of our application once it gets into deployment. This is also how we're able to action on the concept of shifting our security to the left. And the security also should be continuous. All right, so key takeaways here are that DevSecOps allows us to bridge silos between business units. It allows us to be more proactive with our security. And it also allows us to be efficient in our application development and save both time and money by having earlier detection of problems. In this lesson, we talked about the DevSecOps cycle and how to effectively integrate security and operations into our development lifecycle. Thanks for joining. I'll see you in the next lesson. Welcome to the final lecture of Module 1, which is on the verification and certifications using common standards. As you might have guessed, in this lesson, we're going to be talking about verification using common standards, as well as some system product certifications in the industry. So the first set of standards we'll talk about is going to be the International Organization for Standardization, or International Electrotechnical Commission. You don't need to memorize this name, but what you should be familiar with is this abbreviation right here, which is ISO/IEC. This organization has a variety of standards, starting with the ISO 27001, which is a standard that's going to help us establish an Information Security Management System, or ISMS. So they should be used by organizations to build their own ISMS. To complement that, ISO also has 27002, which is a framework to help build related security controls to enforce the standards that we came up with in the ISMS development. For cloud-specific controls, ISO has 27017, and then even more specifically, we have the ISO 27018, which is privacy controls within the cloud, which is governing things like PII. Next up, we have the payment card 18, which is privacy controls within the cloud, which is governing things like PII. Next up, we have the Payment Card Industry's Data Security Standard, or PCI DSS. It's really important to understand that PCI DSS is not a law, it's just a standard built by commercial organizations. These commercial organizations are many of the different organizations across the US that provide the credit that is backing your credit cards. So for any organization that is processing credit card transactions, it's a contractual requirement with these credit backing agencies that they are handling these transactions securely. There are 12 requirements within the standard aimed at reducing payment fraud, which is what helps reduce the risk faced by the organizations providing that credit. The standard also focuses on isolation, least privilege, and auditing. Okay, next up we have some government cloud standards. The first one is the US FedRAMP standard, which was developed by the US government, and it allows us to assess our cloud security systems and services and ultimately gain an authorization for government organizations to use it. Another one is going to be the UK's G-Cloud, which is a government-managed marketplace for applications, and they provide a framework for applications to become approved to be sold on this marketplace. The next one is going to be the Cloud Security Alliance's, or CSA's, Security, Trust, Assurance, and Risk, or STAR. The most unique feature of this particular standard is going to be that it's focused on CSPs, not cloud service customers. So there's 2 assurance levels within the STAR, and it's going to be level 1, or a self-assessment, and then level 2, or a third-party audit. This 2-tier system allows for flexibility for CSPs to achieve one or both levels of the STAR standard, while also providing confidence for customers of these CSPs that the CSP has achieved these levels of security. There are 2 supporting products of achieving STAR certification, which is going to be the CSA's Cloud Controls Matrix, which is an incredibly robust set of controls that can be applied within the cloud, as well as the CAIQ, which is similarly long questionnaire, which helps you establish how well you are meeting standard security requirements. All right, the first system product certification we'll talk about is going to be the Common Criteria. The Common Criteria is an international guideline that allows us to evaluate our security. We have these different levels that we see on this graphic over here, and these are evaluation assurance levels, or EALs. And each level is a different gauge and testing rigor. However, it's super important to understand that these levels don't necessarily directly equate to security level, but rather appropriateness of the testing for the product's purpose. Another key feature of the Common Criteria is that it should be conducted by an independent lab. All right, finally, we have the Federal Information Processing Standard, or FIPS 140-2. And anytime you see FIPS 140-2, you should be thinking about encrypting data. This standard has been fairly widely adopted despite being developed by the US government, largely due to the US government's influence in the field. FIPS 140-2 establishes clear criteria for strong data security controls, as well as specific testing for cryptographic functions. What you should take away from this is that depending on the security requirements and sensitivity of the data that you're securing, FIPS 140-2 is going to help you establish clear requirements for encryption algorithms that should be used to secure that data depending on the sensitivity level. This version of the FIPS 140 standard is nearing the end of its life cycle, and it's scheduled to be retired in 2026 and will be upgraded to the FIPS 140-3 standard, which will come with solutions for addressing modern challenges, such as the possibility that quantum computing will render current encryption algorithms obsolete. In summary, we've talked about a variety of different standards that allow us to verify and certify our cloud infrastructure. Thanks for joining. I'll see you in the next module. Welcome to Module 2 of this course, and in this module, we'll be talking about cloud data security.